So I've got this family of initial value problems. Y double prime plus y equals f of t. So that's going to be my forcing function for this harmonic oscillator. I'm going to make sure that my initial condition is that my initial position is 0 and my initial velocity is 0. Okay. So here are the directions. We're going to solve this using convolutions. So step 1, we're going to find z, which will be the solution if my forcing function is the Dirac delta function at 0. So impulse forcing at 0. And then we're going to use convolutions to find y, which is the solution if the forcing function is cosine of t instead. Okay. So what I know is that the Laplace transform of z is 1 over s squared plus 1. I got that really fast. That's because in the last video we took a look and we said, hey, the Laplace transform of this is just 1. If I have a second order constant coefficient, left-hand side for my linear differential equation, like so, with this initial condition, then the Laplace transform on the left-hand side will just be the Laplace transform of my function, and I'm calling my solution, in this case, z rather than y, times the characteristic polynomial for this, which would just be s squared plus 1. The same thing that I set equal to 0 to get the characteristic equation if I'm finding the associated homogeneous equation. Now, if I want to actually take the Laplace transform of both sides of the equation and get that, I can. But we proved that in general, that if I take y double prime, well, actually, if I take ay double prime plus by prime plus cy equals the Dirac delta function at 0, that what I'm going to get is that the Laplace transform of y will be 1 over as squared plus bs plus c. So we've proved that in general, so we can actually use that. Now, I still need to do a little bit of work because I need to calculate z. So z is going to be the inverse Laplace transform of 1 over s squared plus 1. But that's just sine of t using formula 2. That 1 is 1 squared. So the formula on your formula sheet is sine of omega t, but my omega here is 1. 1 squared is 1, and I've got an omega, or a 1, on top. Okay. So z is sine t, and so now I'm ready to say, okay, so I need to calculate the solution here, which will just be f star z. So that's going to be cosine of t, that convoluted with sine of t. So let me remind us what the formula for the convolution is. So if I'm looking at f star z, that's the integral from 0 to t of f evaluated at t minus u times z at u du. So let's write that out with our particular functions. F was cosine, so we're going to get the integral from 0 to t of cosine of t minus u times z, we said, was sine, and we're evaluating that at u, and then integrating with respect to u. Okay. Now, this looks a little bit tricky, of course, because I have different inputs to my two different trig functions. This is cosine evaluated at t minus u, that's sine evaluated at u, but it's trig. With trig, there's always an identity to save us. And the identity that will save us is the difference formula for cosine. Okay. Now, I don't like to memorize formulas, so I know the sum formula for cosine. So I'm going to just run through real quickly the sum formulas for both sine and cosine. So sine of a plus b is sine a cosine b plus cosine a sine b. Cosine of a plus b is cosine a cosine b minus sine a sine b. Good formulas to know. Okay. Now, basically this says that both sine of a plus b and cosine of a plus b can be built out of four functions. Sine and cosine of a, and sine and cosine of b. So if I know those pieces, I can put them together to build sine of a plus b and cosine of a plus b. Now, these can be proved in various ways, but I have sort of a silly mnemonic device that helps me to remember them. So the key is that sines are the social functions. Okay? They're very social. So when they're in charge of the party, they like to mix it up. They like to talk to the other trig functions. So you'll see sines and cosines socializing together. This is, of course, a very positive quality. So we applaud this. Okay. Cosines. Oh, very antisocial. When cosines are in charge of the party, they stick with their own kind. That leaves the sines with nobody to talk to but the other sines. They're probably talking about how mean and nasty the cosines are. Not only that, the selfish bastards put themselves first, and that is a very negative quality indeed. I wish I had come up with that. It was actually a former student of mine who came up with that. I'm so proud of her. Okay, but I will never forget these now. Okay, so how does that help me out here? Well, I'm just going to rewrite this as, I can think of this as cosine of t plus a negative u. So that's going to be cosine of t times cosine of negative u minus sine of t times sine of negative u. And all of that, that was cosine of t minus u, all of that is times sine u, and then we've got to integrate. Now I'm going to use the fact that cosine is even, so cosine of negative u is just the same as cosine of u. So this is the integral from 0 to t, cosine of t times cosine of u. Sine, however, is odd. So sine of negative u is the opposite of sine of u. So that's going to mean I can basically put another negative sign in front here. That becomes positive sine t sine u. And all of that is times sine u du. So now I can distribute this sine u. So we've got the integral from 0 to t, cosine t, cosine u, sine u, plus sine t, sine squared u, du. Now, remember that t is constant with respect to u, so I'm totally fine having t as one of my angles, but the only angle that's a variable now that I'm plugging in is u. Okay. Here, I had two different inputs to my trig functions, which I like to think of as angles, okay, but they were both variable expressions because they both had a u in them. Now the only variable expression is just u. So I'm going to split this up into two integrals. So we'll have the integral from 0 to t of cosine of t times cosine of u times sine of u du, plus the integral from 0 to t of sine of t times sine squared of u du. All right. So here I'm going to factor out the cosine of t because that's constant with respect to u. And then I'm just going to do a quick w sub. Let's let w equal sine u. So dw is cosine u du. So this is going to become the integral then from sine of 0, which is 0, to sine of t of just w dw. Plus, now here I can factor out the sine t, integral 0 to t, sine squared u du. Yeah, I'll derive that for you. Okay. So for sine squared u, if you're taking 3c, you're very familiar with this. If you've taken 3c recently, you're very familiar with this. If it's been a while since you worked with this, you might have forgotten it. But if I'm integrating an even power of sine or cosine, the key is to use the double angle formula for cosine. Okay. So that's to say cosine of 2u. Now, I'm going to just use the fact that that's cosine of u plus u. So now I can use that sum formula, right? Cosines are antisocial, so that's cosine u which is cosine squared u, minus sine u, which is sine squared u. Okay. So I've got cosine of 2u, which is easy to integrate, is cosine squared u, which I don't care about, minus sine squared u, which is what I want to integrate. So I'm going to replace this cosine squared with 1 minus sine squared u, minus another sine squared u. So we've got cosine of 2u is 1 minus 2 sine squared u. And if I solve for sine squared u, I'm going to add that over, subtract over the cosines, 1 minus cosine 2u, and divide by the 2. Okay. So here, actually let's just clear some space. Here I'm getting cosine of t times w squared over 2 evaluated between sine t and 0. Plus here I'm getting sine t times the integral from 0 to t of 1 minus cosine 2u over 2 du. All right. So for this one, I'm going to get cosine of t times sine squared t over 2 minus 0. Plus here, now I'm going to do a quick substitution. Let's see, what letters have I not used? I haven't used v yet, so we'll use v. Let's let v equal 2u. Then dv is 2 du. That's a 2 on the bottom. That's not helpful. So I'm going to introduce a 2 on the inside, counterbalanced with a 1/2 on the outside. And I'm also going to just factor out that 2. So that's going to make that a sine t over 4 on the outside. We'll be integrating from 0 to 2t, and we'll be integrating 1 minus cosine of v dv. So this is cosine t sine squared t all over 2, plus, let's see, sine t over 4 times v minus sine v evaluated between 2t and 0. Okay. So that is cosine t sine squared t over 2 plus sine t over 4 times, when I plug in 2t, I'm going to get 2t minus sine 2t. And then when I plug in 0, I'm just going to get 0. So let's just write that a little bigger somewhere. So that was what we were calling y. That was our solution when our forcing function was cosine of t. And what we've gotten now is that's cosine t sine squared t over 2 plus, I think I'm just going to distribute this. So the 2t over 4 I can cancel. So I'll get t sine t over 2 minus sine t sine 2t over 4. Now, if I wanted to simplify that further, I certainly can, because I could use the double angle formula for sine. In fact, let's just do that, because I think that might give us some stuff that's going to combine, but I'm not sure. So let's see, cosine t sine squared t over 2 plus t sine t over 2 plus sine t. Now sine 2t is just 2 sine t cosine t. And that's all over 4. Now notice I can cancel a 2 here, but then this term right here is sine squared t cosine t over 2. I can combine that with this cosine t sine squared t over 2, so that I'm going to get one full copy of cosine t sine squared t plus t sine t over 2. Now that last bit was some optional simplification. I would have been fine with you stopping here. You had a correct answer. You'd finished evaluating the convolution. But I could just see it looked like I was going to be able to condense this down to 2 terms, so I wanted to keep going.